Math 1314, Tyler Junior College, section 3.3, dividing polynomials, remainder and factor theorems. In the previous video, we introduced how to do long division. And it's long, hence the name. But the steps in it mirror the steps for numerical long division. So if you're ever doing a polynomial long division problem and get stuck, ask yourself, what would I do next if this were just a number division problem? However, long division has some issues. And I've managed to find an example that covers both of them. For example, we're going to divide 6x to the fourth plus 5x to the third plus 3x minus 5 by 3x squared minus 2x. So what are the two issues? Issue number one. For lack of a better word, chunkier divisors. And by chunkier, I actually mean two things. Number one, the degree of the divisor is more than 1. So it's not just linear. Number two, the leading coefficient is not 1. So more x's and a number in front of them. Now that doesn't change what we're going to do. That just means we got more stuff to deal with. The other issue is something that must be dealt with. Well, there's a way to not deal with it if you're extremely cautious, but I would rather deal with it so I don't have to be extremely cautious. The other issue is missing terms. Now, what do I mean by missing terms? Well, if you have a polynomial, it's going to have a highest power, a degree. And if the polynomial is written in general form, then it's from the highest power to the lowest power. And normally we would expect every power to be represented. For example, this is a fourth degree polynomial. So if the highest power is 4, we expect the next power to be 3. And then we expect the next power to be 2. There is no power of 2, it's missing. After that, we would expect the next power to be 1, and then finally a constant term. This divisor is missing its x squared term. Even the dividend is missing something. It's a second degree polynomial, so its highest power is 2. We expect the next power to be 1, and then we expect a constant term. This has no constant term like a minus 5. If you are doing a polynomial division problem and there are missing terms, if there are missing terms, so we'll put a question mark here, you represent with a 0 coefficient. So you literally state that there are no x squareds, and it would look something like this. There's a reason why you have to account for missing terms. The divisor is 3x squared minus 2x, but it's missing its constant term, so we're going to write plus 0 to represent it. The dividend is missing its x squared term. So when we get to the x squared term, we're going to represent it with a plus 0 x squared. Literally saying that this has no x squareds. Don't forget the rest of the terms. The reason you want to represent missing terms with a 0 coefficient is pretty self-explanatory once you get into it. But just to let you know, it's to preserve like terms being lined up. I'll show you what I mean. Let's begin the division process. How many times does the leading coefficient of the divisor go into the leading coefficient of the dividend? Well, let's just go to the side and stack them on top of each other. 6x to the fourth over 3x to the second. The coefficients get divided, so 6 divided by 3 is 2, but the exponents get subtracted, so 4 minus 2, well, that's also 2. So the first term in the quotient is 2x squared. We'll write it here. And now I have to multiply everything by 2x squared. 2x squared times 3x squared, 2 times 3 is 6. X squared times x squared is x to the fourth. Next, 2x squared times negative 2. 2 times negative 2 is negative 4. X squared times x is x cubed. And then 2x squared times 0, well, 2 times 0 is 0. and then the x squared. Now here we really wouldn't have got a misalignment of terms because had we not represented missing terms, that would have been missing and so would both of these. So it would have been okay, but watch what happens in the next round. Well, first we got to subtract. But to subtract, I would recommend changing all the signs and then combining like terms. So the 6 becomes negative, the 4 becomes positive, the 0 becomes negative, and then we combine like terms. The leading terms cancel, but that's supposed to happen. 5x cubed and 4x cubed is 9x cubed, and more specifically, positive 5x cubed and positive 4x cubed is positive 9x cubed. And then the x squared terms, well, 0x squared minus 0x squared is still 0x squared. You could argue that they cancel, but I'm intentionally trying to represent every term, even if it's missing. And then we bring down the positive 3x. And then we do it all again. Divide one leading term by the next. How many times is 3x squared going to positive 9x cubed? Well, let's put positive 9x cubed on top of 3x squared and see what happens. Positive divided by negative is positive. 9 divided by 3 is 3. And we subtract the powers, so 3 minus 2 gives us 1. Positive 3x to the first power, or more simply, positive 3x. That's our next multiplier. Now we'll see why the missing terms being represented are important. Positive 3x times positive 3x squared is positive 9x cubed. Okay. If the missing terms were not represented, this column would not be here, so the next written term would be positive 3x. But the next part of our multiplication is positive 3x times negative 2x. Positive 3 times negative 2 is negative 6. X times x is x squared. Again, had we not represented missing terms, none of these zeros would have been here. Everything else here would have been shoved over into its place. This 3x term would be sitting above this negative 6x squared term. Those are like terms. We would be stuck in a sense. So representing missing terms preserves the alignment of like terms during the long division process. We still have one more multiplication. Positive 3x times 0 is positive 0x. Time to subtract. So change all the signs on the second, change all the signs on the product we just found. So positive 9 becomes negative 9, negative 6 becomes positive 6, positive 0 becomes negative 0. And then combine. The x cubed terms cancel, but if they didn't, something went wrong, so they should have. Next, 0x squared and 6x squared is 6x squared, more specifically positive 6x squared. And then positive 3x minus 0x is still positive 3x. One more time. Bring down the minus 5. And figure out what goes next in the quotient. How many times is 3x squared going to positive 6x squared? Well, let's put positive 6x squared over 3x squared. Positive 6 divided by 3 is positive 2, and the x squareds cancel. So the last term in our quotient is just going to be positive 2. And now to multiply. Positive 2 times 3x squared is positive 6x squared. Those match, but I was expecting that. Positive 2 times negative 2x is negative 4x. Positive 2 times positive 0 is positive 0. Change the signs. So the plus 6 becomes a minus 6, the minus 4 becomes a plus 4, and the plus 0 becomes a minus 0. Leading terms cancel. 3x and 4x is 7x. Negative 5 minus 0 is negative 5. At this point we're done because there are no more terms to bring down, and you might be a little curious as to why this remainder isn't just a number. When you're doing polynomial long division, you stop when the degree of the remainder is less than the degree of the divisor. In fact, the degree of the remainder will always be less than the degree of the divisor. Since this divisor was degree 2, the remainder had to be either degree 1, which it currently is. It's possible it could be degree 0, meaning a constant term. But you stop when your remainder has a lower degree than your divisor. Speaking of the remainder, we still do the same thing with it that we did before. We add the remainder on top of the divisor, and in this case, there's no need to represent the 0 anymore. So the answer to the division problem is 2x squared plus 3x plus 2 plus 7x over 3x squared minus 2x. So watch out for chunkier divisors, but using this technique of stacking leading terms and reducing them will always help you figure out the terms in the quotient. And if there are any missing terms, make sure you represent them with a 0 coefficient. It preserves the alignment of like terms.